All right, for worksheet 3, applying the first fundamental theorem of calculus, definite integral as a total change. Just want you guys to notice right here, this is the fundamental theorem of calculus, sometimes abbreviated to FTC. I want you to also notice the alternate forms. If you start with the FTC in this format, okay, what happened to go to here? You can see that we've isolated f of b. So this is the y value on the antiderivative at the x value of b. So all we had to do was just add f of a to the other side. So what this is saying to us is the y coordinate at b is actually equal to the y coordinate at a plus any change that occurred from a to b. Here's another alternate form of the FTC here. Notice that f evaluated at a is isolated. Okay, so if f of a is isolated, algebraically, you could add this to the other side, okay, and make it a positive value. But then you'd have to subtract the integral from a to b. And that's exactly what happened here. So these two are just different arrangements of the fundamental theorem of calculus. And sometimes we're going to be wanting to find a y value on the original graph given a y value on the original graph also. Okay, and we'll be able to use these alternate forms to find either f of b or f of a. So our accumulated change is given by the definite integral, whose integrand is the rate of change. And all this means is you're integrating, the integral symbol, you're integrating a rate. This is a rate, this is a derivative. It doesn't have that nice little prime notation, but somehow in context, we are told that f of t is a rate of change. So more specifically, if f is the rate of change of uppercase f, okay, then these up here hold true. And that's all I meant by then. All right, in these exercises, we're going to be interpreting the meaning of a definite integral. All right, if h of t is the rate of change, so right there they're telling you that h of t is a derivative. And it's the change at which the height of a conical pile of sand is changing. It's measured in feet per hour. So if you didn't catch rate of change here, with these words and it being a derivative, h of t being a derivative, then feet per hour, the unit should indicate it's a derivative. All right, so what does it mean for us to integrate from 0 to 5 of h of t dt? And make sure to answer in correct units. Okay, I take the integral and I write it down again, and I write down the word means. This integral means, and it means the answer that results from this. Okay, when I integrate this rate, I get back to the original quantity. When I integrate a rate, I lose the rate and I get a change. So if that helps remind you how to begin the explanation, explaining the meaning of this integral, then that's wonderful. All right, this means the change. So the answer to this, when I integrate a rate, I get back to change, means the change. All right, and let's put some context, okay, to this. Well, it's a change in what? Well, it's a change in the height of the conical pile of sand. Okay, so we're going to try and do a template here. Okay, the answer to this integral, we're going to get back to a change, and it's the change in the height of this sand. Okay, right here would be a good time to put the units, because notice this. This is answer in correct units. Well, the height is going to be measured in feet, because we'll lose the per hour. So I'm going to put in feet. It's the change in feet. Okay, we're not done. We also need to address the limits from time equals 0 to time equals 5 hours. If you're asked to explain the meaning of an integral or what does an integral mean or represent, okay, this is a good template. Okay, write down the integral, say it means when you integrate the rate, you're losing the per hour and you're having an answer of feet. Okay, but based on what time interval? Because this matters too. So two things. Okay, what does the answer give you? A change in feet of the height. Okay, and based on what time interval? So look at the limits. So the answer and the limits. So let's look at number 2. Okay, v of t is a velocity. It's a rate of change of position. It's moving along the x-axis. Okay, and the rate is measured in feet per second. So what is the meaning of this integral? So integrating a rate, you lose the rate. Well, when we lose the rate, it's per second. We're back to feet. So it means the change in distance of a particle so I'm just putting some context to it right here. It means the change in distance of the particle, and make sure you put the units in feet. We're not done. Let's talk about the limits from t equals 3 to t equals 10 hours. Seconds. All right, example 3. Right, b of t is a rate of growth, so right there we know it's a derivative. It's a rate of change. B of t is the rate of growth of the number of bacteria in a dish, measured in number of bacteria per hour. What does the value of that integral represent? So remember, integrate a rate, which this is a rate, we lose the rate. So it's the growth in the number of bacteria in a dish. You could put the word growth, or you could put the word change. Change is kind of all-encompassing. We were told it's a rate of growth, so we know the bacteria are growing, but I'm just going to put means the change. You could put means the growth. Both are correct. Means the change in the number of bacteria in a dish. All right, measured in, like up here, I put measured in feet. Well, what is this measured in? Well, it's measured in numbers, so I'm not going to go ahead and put comma in numbers. I could, it wouldn't be wrong, but it'd be kind of redundant. It just means the change in the number of bacteria in a dish from, let's talk about the limits, t equals 2 to t equals 6 hours. Okay, and on 4 and 5, I kind of change it up a little bit. All right, if v of t is the velocity of a particle moving along the x-axis at time t, and the position x of t is 5 at time equals 2, let's stop right here. Another way to interpret that is to say, okay, well, x, its position evaluated at the input of 2 seconds is 5. This is what we call an initial condition. This is a point on the antiderivative of the velocity graph. So here's your rate, here's your regular function right here. It's just we're using v and x instead of, say, f prime and f. So anyway, this is kind of what we call an initial condition. All right, write an integral expression. All right, I know I'm going to need an integral that represents the position of the particle at time equals 10. So I want to know where is it located. So I'm saying, okay, well, what's its position at time equals 10? So really, what we're saying here is, let's find x of 10. What's its location? All right, so if I'm going to use an integral expression that represents the position at time equals 10, okay, I'm going to come down here and say, okay, well, x of 10, its position, well, let's take what we know about its position at 2 seconds, which is 5, and let's add any change to its position in the time interval from 2 to 10. So these are like your limits here, 2 to 10. So its change in position would be given by integrating the rate or integrating velocity. So 2 to 10, v of t, dt. So we could find its position by taking 5, which we know is x of 2, and adding it to this answer right here, if we could find it. And if you think about it, at the very top of this worksheet, if I were to rearrange this and just bring over x of 2 to the left side of the equation, this is the fundamental theorem of calculus. It's a change in two values on the antiderivative. And we know that's equal to the area under the curve, or the space, I guess we should say, the value of the integral from these two limits right here. All right, so this is the answer for this problem. All right, question B has us look at writing an integral expression that gives the total distance traveled by the particle on that time interval. Well, easy enough, 2 to 10. Remember, we want to take into consideration that this particle may have traveled, both left and right. So we'd want to take any part of the velocity graph that's negative and make it positive. And we can accomplish that by writing an integral expression that involves the absolute value signs. 5. If lowercase p of t is the rate of growth, so derivative right there, of a rabbit population measured in rabbits per year, 100 rabbits in the year 2005. Notice it's t equals 0. They're coding your data. So what I can do is I can interpret right there, that is my initial condition. The uppercase P population at 0 or 2005 was 100 rabbits. Write an integral expression that represents the rabbit population 2 years later. All right, so the population at t equals 2, well, what I started with, my initial condition, my 100 rabbits, plus any change that occurred in those 2 years by integrating the rate, the lowercase p of t. So that's an integral expression that represents the rabbit population 2 years later. And again, like the previous problem, notice if you pulled over p of 0, that's just the fundamental theorem of calculus, just using some alternate notation. All right, so for worksheet number 5, we'll do a couple examples together, but we'll have to be in the next video.